Well, to continue with our previous discussions, where did we end? I had mentioned that normally this is very good, but under certain circumstances we found that there is good amount of deviation. Therefore, to improve predictions, people started thinking about any particular third parameter which can be incorporated here, which takes into account intermolecular interactions, that is expected to improve the 2 parameter law of corresponding states. So, people started thinking about the third parameter. What did they observe? The first thing which people observed is that if really all gases obey this 2 parameter law of corresponding states, then from here all gases should have the same value of Zc. So, what they did, they started finding out Zc for a large number of values which I have shown here. If you observe, you find that the Zc values for the different gases, they are definitely close to one another, but there is a variation if you observe here, that too these are mostly for non-polar molecules. The variation is from 0.26 to 0.3. The variation occurs in this particular way. So, therefore, people thought that definitely the third parameter should be something, or rather the third parameter should be the critical compressibility factor, where for 82 compounds when Zc was found out, it was found that Zc was varying from 0.23 to 0.30, with the majority of the cases lying between this particular situation. So, therefore, it was thought that when any gas obeys the 2 parameter law of corresponding states, they should have a Zc average of 0.27, and whenever there is a deviation for this, then Zc should be introduced as a third parameter, and accordingly the third parameter law of corresponding states was introduced, and a lot of graphs of Zc were there, and this was Zc equals to 0.27. Any deviation was taken into account by separate graphs, right. This was one class of thought. This particular class of, or rather this particular definition, it was given by the it was given at the University of Wisconsin. But the more popular approach is the thing which was given suggested by the University of California. What they suggested, they thought that if the gases, they correspond to the law, to 2 parameter law of corresponding states, then all the gases, they should have the same saturated reduced pressure, saturated vapor pressure at the same reduced temperature, right. So, therefore, for this particular case, again if I bring the 2, if this is applicable, then all the gases, they should have the same PR saturated at same TR, this should happen, but people found out that this is not the case, right. And this particular deviation was taken up as the third parameter in the 3 parameter law of corresponding states. How was the deviation, or how was this third parameter brought about? The third parameter was brought about by plotting, if you find I have made it here, by plotting log of PR saturated with 1 by TR. This is actually PR saturated, right. So, therefore, they plotted log 10 PR saturated as a function of TR, and then they found that for different gases, the slopes of these curves, they were different, and they assumed that definitely a perfect molecule should be one with completely spherical molecules, that should be a perfect gas. They assumed argon to be a perfect gas, and therefore, they thought that the limiting value of omega should be such that omega equals to 0 for perfect gases with spherical molecules like argon. Accordingly, they defined omega in the way that I have mentioned here. This was the definition of omega, which gives minus log 10 PR saturated at TR equals to 0.7 minus 1.0. Why? Because for argon we find this term becomes equal to 1 under for argon, and therefore, omega becomes equal to 0 for argon. So, they took up omega as an, this is known as an eccentric factor. This is known as an eccentric factor, and this gives you the deviation of the intermolecular potential of any molecule from that of a simple molecule with spherical, or rather simple gas with spherical molecules, right. And this was taken up as the third parameter in the 2 parameter law of corresponding states, which gave us Z equals to TR, PR and omega. And the functional form relating Z with TR, PR, omega was something of this sort. Z, where this is the Z0 predicted from 2 parameter model, right, and plus omega Z1 TR, PR. This is the functional form relating Z with TR, PR, omega, which gives you that for normal circumstances far removed from the critical conditions and the saturation curves, for more or less not very polar molecules, Z can be obtained from the 2 parameter law of corresponding states. When there is some deviation, then we need to find out omega. Omega can be found out from the slope of PR log PR saturated versus TR curve, and then we need another set of equations to find out, just like Z versus TR PR, we need another set of equations to find out Z1 as a function of PR with TR as parameter. So, therefore, along with Z0, additional similar curves were generated for Z1, from which we can find out Z0 and Z1 for any particular gas, evaluate its omega and accordingly calculate the compressibility factor for that particular gas. Here I have, just for your reference, I have presented the Z1 curves as well along with the Z0 curves. If you observe, we have the Z0 curves here and we have the Z1 curves here and the omega curve here. With all those things, we should be in a position to predict the behavior of any particular gas, even if you do not know which equation it corresponds to, simply by assuming the 3 parameter law of corresponding states for greater accuracy and 2 parameter law of corresponding states for most practical applications. Now, this was all about the law of corresponding states and the use of compressibility factor charts and the cubic equations of state. We need to remember that the cubic equations of state, after all, they are approximate in nature, right. Despite all their great advantages, they are approximate in nature, number one, and they have certain empirical constants. Now, a better theoretical basis, or based on a better theoretical basis, the Virial equation of state has been proposed. What is the Virial equation of state? Let us see. Possibly all of you are aware of this particular equation of state. It can be written in a pressure explicit form as well as in a volume explicit form, as we have noted here, and we find that these particular constants, this B, C, etc., these particular constants, they give us the interaction between two molecules, 3 molecules, etc. Now, if you observe this equation, what do you find? The first thing is, this equation has got some theoretical basis, it is not entirely empirical. The next thing is, you find that more or less for very low pressures, high temperatures, you can neglect all the terms, PV by RT becomes equal to 1. So, it reduces to the ideal gas behavior. When it starts deviating from ideality, the deviation is not very high, we can just include the first parameter here. When the deviations are still higher, we can include the higher order terms. So, therefore, depending upon the situation, we can include more number of terms and thus incorporate the extent of deviation from non-ideality just by using one particular equation. Now, the first thing is, and the other important thing I also mentioned, that the constants can be evaluated from intermolecular potential even when we do not have any particular experimental data. Now, usually for the conditions which we come across, we find that usually the first constant, the B and the B primes, they are mostly important. We usually for most practical purposes, we can use the Virial equation by truncating after the second term. So, therefore, this particular portion usually is sufficient for us. and the relationships between the different constants have also been mentioned in this particular equation, right. So, therefore, there is not much that I have to say about the virial equations of state. There is just certain things which I would like to mention regarding the first constant, which is usually much more important and which is of much greater concern for us. Now, if you observe this particular constant, what do we find? There are certain important things that I would like to mention. First thing is, if you take up this particular equation, what do you find? You find that your B, this is simply nothing but limit rho tends to 0 del z del rho at constant t equals to 0, right. So, therefore, what does it imply? It, and we know this B prime, this is the relationship between B and B prime is that B prime, this is equal to B by R t, fine. So, therefore, if suppose we are plotting from this particular equation, if you say, if you are plotting Z versus P, what do you get? You get a linear equation, you should be getting a linear equation at low to moderate pressures, where we can just consider this part. At low to moderate pressure, we find that if we plot Z versus P, we should be getting a linear plot whose slope should be given by B prime or whose slope should be given by B by R t. So, therefore, if we are plotting in this particular case, then we find that the slope in this particular, for each of the equation, what is the slope equals to? Slope is nothing but equal to B by R t. Remember one thing, all these B's and the C's etc., all of them are functions of temperature and they are independent of the pressure or the density of the particular gas. Again we find that if we plot this particular B, this is B basically, if we plot this particular B with temperature, we find that for very low temperatures the B is negative for all the gases, and then at under one particular temperature we find that the B becomes equal to 0. What does it imply? For low to moderate pressure, it implies that definitely the B is 0 means the gas is behaving ideally. So, therefore, it appears that at the condition for or the temperature for B equals to 0, the gas behaves ideally. It is actually not so. At the condition of the temperature for B equals to 0, the attractive and the repulsive forces are equal to one another, and this happens at a specific temperature, which is again a property of the gas, and this particular temperature is known as the Boyle temperature. This is known as the Boyle temperature, often denoted as this temperature. For each particular gas, this temperature is denoted by Tb. For this particular case, we find that the attractive and the repulsive parts of intermolecular attraction cancel and the gas appears to behave ideally, provided we have neglected the effect of virial coefficient beyond the second. So, therefore, all these things are applicable for low to moderate pressure. So, naturally finding out the first virial constant, it is quite important, and there is a very easy way by which we can find it out. Again, for understanding the very easy way, we refer to the basic equation. What is this? This is equal to B prime, this is equal to 1 plus B by R t into P. Agreed? Now, if you multiply both sides by R t by P, what do we get? We get V equals to V 0 plus B as a function of, it is a function of t. From this, what is B equals to, can you tell me? It is nothing but equal to V minus V 0, which is nothing but equal to the residual volume for that particular gas at the pressure, at any particular desired pressure. So, therefore, we can find out data on the second virial coefficient from the data of residual volume if it is available at any particular pressure conditions, provided we can neglect the contribution of third virial coefficient and higher terms. So, therefore, these are some of the few things that I wanted to tell you, but before I end, there is something interesting that I would like to mention. I have already told you that when we are using the virial equations of state, when we are using the Virial equations of state, I have already told you that usually we are dealing with the first two terms, or we come across the first Virial coefficient, which is important. And I have also highlighted, just because the first Virial coefficient, and one more thing, for most of the cases this particular form is much more convenient. So, we are mostly dealing with the coefficient B, and I have also shown you the physical significance of B. Now, there is something interesting which I would like to tell you. While for normal circumstances the Virial equation with two terms is sufficient, at the critical condition we need at least 3 terms for a proper representation of the PVT behavior. Let us see how and why. I would like to show you that how near the critical condition we use at least the third Virial coefficient for a correct prediction of the PV behavior near the critical point. Let us see what happens if we start with just the two equations of state. We truncate it after the two equations. What is it? This is RT by V plus RT B by V square, right. What is del P del V, sorry, this is P equals to, what is del P del V at constant T? It is minus RT by V square minus 2 RT B by V cube. What is del 2 V del V 2 at constant T? This is nothing but equals to, simply I am performing differentiations and nothing else. I get the equation as this. What happens at the critical point? At the critical point, my T equals to Tc, this T equals to Tc. So accordingly here I should be getting, I would be putting Tc, Vc, I would be substituting all the constants with the critical values, right. So once I do this, and we know that at T equals to Tc both of them are 0. Now just observe the equations closely. From this equation what do you get? You get B equals to minus Vc by 2. From this equation what do you get? Simply solve it and to find B equals to minus Vc by 3. So therefore, you are getting inconsistent results if you are just considering one particular coefficient at the critical point. So therefore, you get inconsistent results and you need to consider more number of terms for a correct prediction of the PVT behavior near the critical point. What do we need to do then? For this particular case, if we consider more than one particular critical constants, then we are dealing with this particular equation, right. Sorry, this is, yeah. So, in this case, if we are performing del V del T, we get minus RT by V square minus 2 RT B 1 by V cube minus 3 RT B square by V to the power 4. Again, if we differentiate it once more, we find out this equation becomes 6 RT B 1 by V to the power 4 minus 12 RT B square by V to the power 5, right. At the critical point, again I would like to substitute everything with the critical constants, okay. And then what do I have? I have got two particular equations B 1 and B 2 in this particular case, or sorry, B and C. I had written them in the form of B and C in this, this is B and this is C, I am sorry, this is B and this is C. So therefore, from these two equations now we find that we have, from these two equations we find that we have come to the state where B is equals to minus Vc and C is equals to Vc square by 3. So therefore, we find that for the critical isotherm, if we substitute these two values, we find that Pv by Rt, which is nothing but Zc, this reduces to 0.33, PCVc by R, this reduces 0.33 at the critical point. So from here, what do we deduce? I deduce that it is fine to use the Virial equation of state with just two terms for conditions far removed from the saturation curve and at the critical point, but for conditions near the critical point, in order to obtain consistent PVT behavior, we at least need to consider 3 terms in the Virial equation of state, right. So, with this more or less I have completed the some of the discussions on the PVT. Achha, one more thing suppose I would like to mention, it is the generalized equations in terms of the PVT behavior, rather in terms of the virial coefficients. Now, here we find that from generalized compressibility factor chart, just the way I have deduced the compressibility factor chart from the cubic equations of state, we should be able to predict the virial coefficients also from the generalized charts. So, we know that z equals to 1 at p equals to 0. So, therefore, we also know that at low pressure z, it is a linear function of p at constant t, right. So, for low to moderate pressures, what do we have? We have PV by RT, this is equals to 1 plus B prime P, this is equals to 1 plus BP by RT, which can be written as 1 plus BPC by RTC PR by TR, PR by TR. For non-polar molecules, we can write it down as BPC by RTC equals to B0 plus omega B1. And when you substitute this particular equation in the equation for Z, we get Z equals to 1 plus BPC by RTC, which is equal to 1 plus B0 PR by TR plus omega B1 PR by TR, right. So, from Pitzer correlation we know Z is nothing but equal to Z0 plus omega Z1, from where we can say that Z0 is nothing but 1 plus B0 PR by TR and Z1 is nothing but B prime PR by TR. And from here we can also deduce that B0 can be obtained as 0.083 minus 0.422 by TR to the power 1.6 and B1 can be obtained as 0.139 minus 0.172 by TR to the power 4.2. Now, these are the generalized virial coefficients, coefficient correlations which are applicable at low to moderate pressures for non-polar gases only. So, therefore, this reduces us to the so that we can also deduce the law of corresponding states using the virial equation just the way that we have done from the cubic equations of state. So, with this we would like to do a few problems so that you get much more conversant with the PVT behavior of gases, and then we proceed to find out how the PVT behavior of gases can be used in the equations to predict enthalpy, entropy, internal energy, Gibbs free energy, Helmholtz free energy and a host of other new parameters that we will be introducing from the PVT behavior of gases. So, this is all for the day, and we proceed and we do a few problems in the next class.